Hey, what's up, guys? This is Ayush. Welcome to Developer. Well, I thought I might make a video about function pointers in general because this thing right here, among a lot of other programming constructs, is something we might be dealing with a lot here on this channel. So I thought let's start somewhere, and this is where we are. So, function pointers. Well, function pointers are just a way for us to store a function in a variable so that we might pass it around or do some unique stuff with it. We can, for instance, pass it around to classes as in their constructors or methods or to other functions as well. So we can pass functions, store it in a variable and then pass it around to constructors of classes, their methods or to other functions as well. Well, technically, it's a pointer to a function which is loaded in the code section of your application's binary. For compiled languages without any runtime like C and CPP, this binary would be your exact code for the most part, apart from some other stuff which the compiler surrounds your application code with for the initialization of it, which would be platform specific, of course, and very minimal. So for compiled languages with managed runtimes like Java and C Sharp, or interpreted languages like JavaScript, Python, etc., this wouldn't be your exact application code, but it still essentially is a pointer or a reference to your function. Let's first talk about an example first. Suppose you're making a game and you're using a library which manages device inputs, as in input from various devices like your mouse, keyboard, gamepad, or whatever. Now, how would the library vendor know what action you want to perform when the library detects that the user has pressed some key, for example, on the keyboard? They obviously wouldn't know the game logic for your game, would they? Even if they would, they wouldn't want to make the library just for you and just for that particular game you're working on now. A library in general should be as extensible as it could and apply to a lot of use cases. Well, at least a handful, and certainly not just one. So the vendor would design their API to expect you to register some callback at the time of library initialization, a method or a function, which could be owned by you, and then they would just call it, that method or that function, whenever they detect any input of that certain kind. Um, and they can, however, register separate callbacks for different kind of device inputs, like one callback for mouse, one for keyboard, etc. They are doing the hard work, man. Initializing DLLs or shared libraries or whatnot, hooking up with them, finding your input devices, detecting input from them. All they're asking you to do is provide them a callback method, and you handle what to do with that input and leave the rest to them. This is one of the use cases of a function pointer. You can store your function which you want the library to call, for example, say keyboard inputs, store it in a variable, and pass it around to the input managing library. That's all. You can trust that library now, that it would call your method whenever there are keyboard inputs coming around. This is an example where you kind of defer the execution of a function to a point in time when it's suitable to be called. You don't know nor can determine with any level of exact certainty about when that situation is going to arise. You can't predict when the user is going to press. You won't be making a game in that case, would you? Well, with that explanation out of the way now, let's see with some examples how some popular languages handle this specific programming idea. Well, we'll start with C first, then we'll move on to CPP and explore other languages as well. For both C and C++, I'll be using this CPP translation unit because you can write valid C code in C++, as you might already know. So let's discuss what function pointers in C look like first. So I'll just quickly include cstdio since we are in C++. We can't include stdio.h. We'll have the main, and then let's declare a function, a very simple function which returns nothing. We'll call it print, takes in nothing, and it just prints hello world. That's it. That's all this function does. So we can obviously call this function like this, but we can also store this function in a variable. that would be the function pointer, can do so by writing as follows. So first need to write the return type of the function to which the pointer we want to get. So it's the print function and its return type is void, so we'll write void. Then we open parentheses, type in an asterisk, then the name of the function pointer or the name of the variable which you want to store the pointer in. It would be something like, for example, if you want to declare an int, um, so this is the part which we are talking about. X, this is the variable name which goes in here. um, let's call it fptr, f pointer for now. Since the print function takes in no parameters, so the next set of parentheses would take in nothing, just as the signature of print function indicates. We can now assign it to print. Okay, we can also assign it to ampersand print, but both syntaxes are equivalent, no difference at all. What this does, now fptr is a pointer to print function. Now we can call fptr. Fptr is now a callable and we can call it just like a normal function. We have stored the function inside of a variable. This can later be passed on to other functions, as we will see in a few minutes. Let's see what this program does. Let's just build it. Since we are in building a C++ translation, it will use G++. Our file is main.cpp. Let's name the output main. Let's add in debug symbols. We might need them later. Now let's run this. As we see, we get hello world printing twice. One from this function and one from this function called over here. Calling fptr in this way actually invokes the print function directly. This kind of syntax looks very clunky, but that is how we declare a function pointer in C. If suppose this print function would have to take an input argument like const pointer message, and if it were printing things like that particular message, we would need to pass that message over here. Also, we would need to update the signature or the declaration of our fptr. Since we are taking in a new parameter, we need to mention that over here. We also now need to update the calling syntax as we did for our print function over here at line number 6. Okay, now this looks fine. Let's build and run this. I'll just combine these two. Saves me some time. Okay, so you get hello world printing again on the console. Now, if this were to return any kind of value, well, int, some of you guys might already know, printf returns an integer. You can look at its declaration. So its declaration is extern int printf. Int is the return type of printf. Okay, so we can get an integer out of our print function. We need to update our function pointer declarations right now, and this would be like this. Okay, you can get a value constant v1 from the first function call. We can also get constant v2 from the second function call, and we can, if we would like, print v1 equals v2, then we would, so ideally we would expect these v1 and v2 to be equal. Let's see if they are equal indeed. Obviously you might have gotten the hang of it, but let's just make this clunky syntax look a bit more beautiful. We can do so. Let's first get rid of this part. So this is actually the declaration of f pointer. We can, if we would want to, declare function pointers by having a particular fptr type and then declare the function pointer just like a normal variable, just like the normal int declaration syntax, and you would just assign it to print like this. This would happen if you would insert a type def over here. Well, we obviously need to get this updated. Now this becomes a type. Need to add a semicolon. Now fptr type is a function pointer type, and you can create function pointers out of it with the normal variable initialization syntax. The type goes first, then the actual variable name, and then assign it to some value. Let's create a function void func and take in this fptr type. We will call it f pointer, fp simply. Then we inside of this body will just call fp. Obviously fptr type takes in a constant pointer and we need to provide it. Let's take that as well as in the function argument message. Yeah, we can just get that over here. We can return it. This fptr type have we misspelled it? Yeah, okay. So fptr type, this declaration is local to main. We obviously need to move it outside main so that this is visible to our function over here. Now this looks fine. This should compile. But before we do that, we need to actually call func with our message. Now we get the output as int out. What we can do is we can just print out the out variable actually. Now this func declaration, main is not aware about the func function which we had declared over here. We need to move its declaration at the top too so that main knows about it and we can call that function over there. Are we missing anything? Yes, we are missing our actual function pointer. Let's provide it. Would be fptr. Let's run this. Okay, we get 12. That was all about raw kind of function pointers. The function pointers in C. Let's quickly look at function pointers in C++. The kind of modern way of declaring function pointers. We'll include functional for this. We'll also go over what lambdas are. Just give me a minute. We'll also include, not include, IO stream. Yeah. Let's again have our print function. Hello world. Now our main function where we'll be actually calling the print function and then get the pointer to the print function. Since we are in C++, in our arsenal we have the very nice automatic type inference, the auto keyword, where we don't need to worry about the type anymore. We can just use auto and call it a day. Give it a name fptr and it would be print. Okay, that is how you can declare function pointer in C++. Well, this is very simple, very easy. You just use print and we expect to get hello world getting printed on the console twice. Yeah, hello world is getting printed onto the console twice. If it comes to actually writing the type so that you can pass it around to other functions, so for that, let's do that. We need to do it. We can declare an std function, and for the thing which goes inside these angular brackets, the actual type instance, it would be, since the function which we are storing the pointer to returns void, so void goes again. Within parentheses, you just declare the arguments which your function takes. Takes none, so we leave it at that. Now we can run it again. Hello world getting printed onto the console twice. That's it. Okay. Again, if your this print function would have to take an argument like a constant reference message and message. We would need to provide this message over here. Let's also provide this message in our fptr, and we will have to update our function pointer declaration as like this. Okay, cool. Let's quickly build and run this. Yeah, we get again hello world printing on the console twice. What next? Let me think. Yeah, just note you can add in variable name over here. It can be different from actual instance of that function which you are assigning it to. So for example, I am naming the reference as MSG over here. You can call it like something like message complete text. The compiler won't sue you. It's not an illegal assignment. It's not nothing like that. It's completely okay and fine to do that. Let's just will run this once again, and you see it works. Now let's go over onto lambdas. Before we go on to lambda, let me create a function real quick which takes in this fptr. Okay, so this will be void func. Let me call this func, and then we will be taking in an std function void const string reference that includes the type information fptr or fp, keeping it different purposefully. Okay. Also, we need to take in an actual const string reference string, and we would call the function pointer as such. We actually need to call the func function too, and we won't make our mistakes once again. We will indeed declare this function signature over here because the compiler needs to see this declaration before it can actually call the func function. Obviously, we need to pass the function pointer. Yeah, let's build and run this, and we should get hello world printing thrice. Okay, as we expected, hello world printing onto the screen thrice. We passed it to another function. Now, what if we hadn't declared this fptr, we hadn't declared this print, and obviously we can't call if we haven't declared. This fptr goes to waste. What if func function to call to inline? So we don't want to create a full-blown function declaration definition and all of that stuff for our func function to call. Just want to specify the body just right here. We can do that by something known as lambda functions. Lambda functions, well, ironically, aren't functions but are anonymous functions. They are lambdas, so they don't have a name. Or you can call, if you want to be technical, R value references for functions, kind of. Like I just spun it up right now. Might be wrong, but it is kind of like that. Now we declare a lambda by providing something known as captures. Then the function arguments goes in over here. The function argument is just a const std string reference tr, and then we just print it stdcout str std and l. That is it. That is our lambda function. That is what entirely the lambda function constitutes. The parameters which a function should take go in here. This part is known as captures, and this thing right over here is the body of your lambda function. This one which I've highlighted. Now it will work just as expected, but now you will get hello world printing onto the console just once. Okay, it runs fine. Let me quickly just discuss what captures mean. So if, for example, if you were to have another string is equals to hi, very simple header. If you somehow wanted to use the header over here, well, we will add a space. If you wanted to use this header over here, how would that happen? Well, since this header is not declared inside of the body of this lambda function, which I am highlighting right now, it is declared inside the main function, which is the caller or the creator of that lambda. We need to somehow pass this header around to this lambda. Since it's out of the scope of this lambda, we can do so by using captures. Captures are used to capture outside world information and put them inside your lambda function. We can capture things by reference. We can capture things by value, copy them, just plain copy. And we can also provide the variable name along with the way we want to handle them. So this is how it looks like. You can also do so. This will be copying it by value. Well, let's just say we want to copy it by a reference for now, and we'll run this. We should get hi hello world printing onto the screen. Yeah, we are getting hi hello world getting printed onto the screen. If we weren't providing this capture over here, and then we get a compilation error, let's still go ahead and try to compile this. Okay, header is not captured. That's clearly the compiler helping you that header is not captured, my man. You need to go ahead and use the captures to actually capture the headers. Okay, so this was it about functions and lambdas, function pointers and lambdas. I'll quickly show you one utility of the function pointers, somewhere that it can be useful for extending the usability of a particular library function. Let's suppose we have a sorting function. We have implemented a sorting library API or whatever, and well, it's a simple, stupid, dumb sorting function. It is no way a fancy sorting function, a comparison sort. It will be sorting arrays. For this purpose, we'll include simple CPP style arrays, stack allocated ones. So we need to create a template function for it. Void sort. No, we need to modify the array inline std array. Let's say we are sorting ins array. So we sort our array. Let's quickly test this. We'll delete everything inside it. We'll have return 0. We'll delete this, all of this. Okay, cool. Now let's have an array, std array int. Let's have 5 as the size of our array. Here are, let's call the sort function with our array. Okay, we also need to be able to print this so we can see that the array is indeed sorted. I'll create a generic array printer function. Cool. Let me just print the array before we sort it and after we sort it. Array, array. So let's just quickly build and run this. Okay, 14597, 14579. Let's just make it a bit more messy, looking a little too organized. 45197. Yeah, let's sort this. Okay, 14579. So the array is sorted. Okay, now what if we want to sort this array in an descending manner? So this current logic sorts the array in an ascending manner. Well, you would say, Ayush, go ahead and change this comparison which you are making. Well, why not use function pointers and let the user decide what kind of comparison they want to make? So let me quickly create an override of this function. Okay, redefinition of sort, since we haven't changed the signature yet. Let me take in a function pointer. We will be returning a bool because we are replacing essentially this kind of the conditional we have. We'll be replacing this comparison with our function pointer. We'll let the user decide by passing in an function, by passing a function from outside. The user will decide what kind of comparisons to make over here. So this will take two ints. We don't need to be modifying them. Const int a, const int b. Cool. That is how the function pointer looks like, and we'll obviously make it call comparison. For example, we'll delete this. Comparison A will be array I, B is gonna be array J. That's it. We've extended our library function. We can now, if we would like, sort this array in descending order. Well, sort descending now. Sorting descending now. Okay. We can sort array. We can provide it via a lambda int a, int b. We can return, instead of a greater than b, we will return a less than b. Let's print our array again. So the third, what is the expectation now we have is that the third array which will be getting printed out on the screen will be sorted in a descending order. Let's just clear this. Okay, there you go. Now we are sorting in descending order. Well, that is how function pointers are implemented in C and C++. Well, that I think would be enough for this video. I'll soon bring a part 2 for this discussion. Meanwhile, you can drop in your suggestions, something which you wanted out from this video, something for the next part, anything which you want. Well, I'll see you in the next video. Till then, keep on learning, keep on growing. Bye bye.